much. It is now my very pleasant duty as president to invite Professor Jens Eggers to give the 2024 Naylor Lecture on the role of singularities in hydrodynamics. Jens is a professor of applied mathematics at the University of Bristol. He received his undergraduate degree in physics from the RWTH Aachen in 1987. In 1990, working with Siegfried Grossmann, he received his PhD from Marburg University with a thesis on self-similar fluctuations in fully developed turbulence. Dr. Eggers' career has been devoted to the understanding of self-similar phenomena. He has made fundamental contributions to the mathematical understanding of free surface flows, in particular, breakup and coalescence of drops. His work is instrumental in establishing the study of singularities as a research field in fluid dynamics and applied mathematics. With Marco Fontelos, he has published a book at Cambridge University Press, which presents a unifying view of singularities in physics, mathematics, and engineering, and aims to make the subject accessible to a wider audience. Professor Eggers is a member of the Academy of Arts and Sciences in Erfurt, Germany, and a fellow of the American Physical Society. In 2017, he has received the Stanley Courson Award of the American Physical Society. Jens was awarded the LMS Naylor Prize in 2023 for his profound contributions to the theoretical understanding of singularities of nonlinear partial differential equations, particularly his construction of explicit solutions of equations that shed deep insight into experiments, from the breakup of fluid droplets to the formation of cusps on free surfaces to shock formation in the Euler equations. I'd now like to ask Jens to come up here and deliver the 2024 Naylor Lectures.
Thank you very much, Jens, for this very kind introduction. It's a great pleasure and honor having been asked to deliver this lecture. I've chose a rather general title to give me a chance to formulate an overview of developments over the last 30-odd years, and in the process, of course, highlight some developments I find particularly interesting. For me, the best place to start is how I myself got drawn into the subject of turbulence, and that was through my postdoctoral advisor, Leo Kadanoff, in Chicago. And at the time, we were all marveling about these pictures of turbulence, in this case, a turbulent jet, which is characterized by an amazing varieties of small-scale structures which are distributed in a very complicated way in space. And a popular idea at the time, and as you've seen in Marco Fontelos' talk to today, is the idea that this complicated small-scale structure might be related to singularities. Namely, if I neglect the smoothing effects of viscosity in the equations of fluid motion, I end up with the Euler equation. And the idea is that the process of generation of small scales continues forever and eventually leads to a singularity of the equations in finite time. Well, this program has been followed for many decades now, and even at the time, our mentor and postdoctoral advisor, Kadanoff, suggested that this problem might be a bit too hard at the moment. His suggestion was, let's make it simple. Let's consider some even one-dimensional examples of singularities, perhaps we can learn something about it for this original problem. And it turned out, following this program, that these supposedly simple examples were quite interesting in their own right and taught us a lot about mathematics, but also their applications in the real world. So let me start with this picture. I think Marco has shown already, which shows a splash of water which rebounds after a drop has fallen into a glass of water. And owing to the action of surface tension, which tries to reduce the surface area, the radius of this fluid neck here goes to 0 in finite time. And the physical idea is that if this neck has become sufficiently tiny, it is completely separated from any externally imposed scale, such as this length here at the bottom of the splash. Therefore, there is no more reference scale to measure the size of the drop by, and we expect and that this evolution here must be scale invariant. So if you have scale invariance of a single scalar quantity, that means it is represented by a power law. And this is indeed what is seen experimentally. So this is a plot of the diameter of this neck here as a function of the time distance to the singularity, which occurs at t0, in a double logarithmic plot. And of course, a power law will be converted into a straight line. And the experimentally observed value is very close to the theoretically predicted value of 2/3, valid in the situation that viscous effects are negligible. Another closely related concept is that of universality. Again, if my singularity evolves on scales completely separated from any externally applied scale, this applied scale can't play any role, and the evolution must be given by the intrinsic structure of the equation. And here I have a very simple explanation, a very simple example of such a universality, namely a pinch-off occurs in this sequence twice, namely here and here. So let me just magnify the neighborhood of this singularity and place it next to this one. And you see that the two are very similar. They're almost identical, which is a priori surprising because, for example, this singularity occurs upside down relative to this one, and the direction of gravity is opposite. However, that doesn't play any role, apparently. And each of these breakup events occurs in exactly the same way, with the exact same parameters characterizing the self-similar evolution. So this universality has an important application in different areas of engineering. And my favorite example is that of inkjet printing. Inkjet printing is still used very widely, of course, in printing itself, but also to produce integrated circuits and in biomedical applications. And in all of these applications, the main desire is to produce drops of an exactly uniform, reproducible size. So this is an experimental sequence of such a drop forming from a jet, which is coming from over here. And you see immediately that the drops are by no means of the same size. Namely, you see that between two main drops here, there's always a much smaller satellite drop, which in turn comes from the presence of a very elongated neck between the two drops. So why does this elongated neck form? Well, this is a direct result of the universal structure of the singularity. Namely, the singular solution is such that it's very steep on this side and very flat on the other side. So by its universal structure, it always forces the shape of the liquid into this elongated form and then forms the satellite. So in order to avoid this, the engineers have to go to great lengths, for example, by finessing the initial conditions such that there is a significant relative velocity of the satellite drop with respect to this drop, and then this merges, and the problem is avoided. But this is a very difficult and hard to control situation. This is another example of a singularity, which is not time dependent, but essentially stationary, depending on a physical parameter. So this is an experiment you can easily do in your kitchen. So this is a viscous fluid jet that impacts into a container of viscous fluid. So you can take olive oil and pour it into a glass, and you will see exactly this shape. Namely, owing to the impact of the viscous jet and the resulting shear, the free surface between the liquid and the air is deformed into this very sharp structure, forming a cusp here, which in this axisymmetric situation is wrapped around the jet here. The point I want to make with this picture, or rather video, you will see now, namely what we've done here is we've increased the velocity of impact a little bit more. And as a result, this cusp structure has become unstable and leads to a secondary structure, which is a sheet of air wrapped around the jet. And this phenomenon is crucial for an everyday phenomenon, namely the entrainment of one phase into another phase. For example, air into the yolk of an egg. That's what you do if you use an egg beater. You use an egg beater, you create a great shear. This shear leads to singularities on the surface, and the tips of these cusp singularities are the entryways, are the seeds for secondary structures, namely this sheet. So this leads me to one more general idea about singularities. Singularities are machines to create small structures. So that's another problem I looked at recently. This is a container of viscous fluid which empties through a hole in the bottom. And this generates a flow which is sketched by these arrows. And this flow deforms the tip into the interface into this very, very sharp tip, which can very easily go down to molecular scales. Why? Because the analysis shows that the size of this tip behaves like the exponential of the flow strength squared, or rather the inverse of that. So the curvature here at the tip behaves like the exponential of the flow strength squared. So if you only increase the flow strength a little bit, you have a tremendous decrease in scale And you can very easily bridge all the way from macroscopic millimetric scales to microscopic molecular scales. So in other words, hydrodynamics is a machine to make small things. Normally, as an engineer, to make a really small structure, you would have to produce a tool, machine a tool, and then work to whittle away the material here to make something very sharp. In hydrodynamics, this can occur automatically, simply by the internal nonlinear structure of the equations. You focus the flow into these very small scales, and to have some somewhat whimsical examples here, if you manage to preserve these structures, you can have very sharp tips here, and here, and use them to your advantage. So after these introductory words, let me come to a summary which has some similarity with what Marco has shown you. So why are singularities interesting? So singularities are the crucial events in the evolution of a flow. For example, formation of a drop where the character of the flow changes. And as you have seen in the instability of the cast, in my olive oil experiment, there are the seeds for new structures. There's universality, and the universality imposes important constraints on the flow. But a very nice summary of this, which I like, is that singularities are the fingerprints of a PD. That means singularities contain all the information you would like to have about the structure of an equation, which is independent of initial or boundary conditions. And finally, as we will see in somewhat more detail now, the underlying mathematical ingredient is a scale invariance or self-similarity. And this mathematical structure will, as Marco has already shown you, lead in many cases to a much simpler and analytically tractable formulation or investigation of the singularities. So here is an example where personally I started from. This is the formation of a drop. Marco has already derived these characteristic scaling exponents. So what do they mean? So this expression means that if I look at the profile of a drop at different times, the shape remains invariant. The only thing I need is to rescale the two axes, the radial scale and the longitudinal scale of my plot, and it will superimpose to a universal profile phi. What is interesting about these exponents is that this exponent here is larger than this one, so T prime is always much smaller than this, which means that in the course of time, the structures become extremely elongated, which you can see here. If you follow this in time, closer and closer to the singularity, you've got extremely thin jets, which are more and more elongated, relatively speaking, in the axial direction. And of course, you have the concept of universality. Universality means in this case that this function phi here has no free parameters. And that means, for example, that if you give me a certain time distance from the singularity, for example, 200 microseconds away from the singularity, I can predict what is the radius of this thread without having been told what the initial conditions are. So that I find a nice illustration of what universality means. But now I will go to an example of such a calculation in much more detail. So I'm not going to use this rather complicated example of the fluid equations and drop pinch off, but rather the very simple problem of a shock wave in its simplest form. Namely, I'm going to treat what's known as Burgers equation or the kinematic wave equation and pursue this program for purposes of teaching you the mechanics of the process. Of course, in principle, I could write down an exact solution to this equation and analyze the consequences of this exact solution, but I'm going to pursue a different way here and rather go through the different steps you would normally pursue. And this kinematic wave equation is a very good model for a shock wave. Here you see a beautiful experimental picture of a shock propagating in a tube. So these lines here mark places of constant density. So you see that the density is much higher here than on the other side. And as time goes on, these lines here become steeper and steeper, which means that the wave becomes steeper and steeper, and eventually there is a jump marked by these dashed lines, and you can count the number of these lines here to see how high this jump is. So there's a finite time at which a jump in density has occurred, and the time where this occurs for the first time, this is what we will investigate in more detail. So, how does the similarity solution, a local similarity solutions to this simple equation work? Everything is expanded around this characteristic time t prime, which measures the time distance from the singularity. So what we do is we write down a similarity solution where once more the idea is independent of time. I only have a single profile, capital U, which is rescaled according to t prime to the alpha and t prime to the beta, where both exponents alpha and beta are unknown. So I plug this into the equation. This is a very elementary exercise in using the chain rule. So there are two occurrences of t prime, so we get two terms. The most important observation is that this exponent is alpha minus 1 because I've taken this and taken one derivative. So the exponent must be alpha minus 1. And there's a second term which comes from here, which is u prime times factors that depend on this rescaling. So there are two factors of alpha because there are two factors of u, and a minus beta because I take in the derivative respect to x, and that gives me a factor of 1 over t prime to the beta. And for this to be a solution, this exponent here has to be the same as this exponent, so I get a relation between the exponent alpha and the exponent beta, which I've plugged in here. So you see that beta is alpha plus 1. But, and this is the similarity equation, which determines the shape of my U. The only problem is that alpha is as yet undetermined. So this is, in fact, an example of self-similarity of the second kind, which normally is harder, but this problem is so simple, we're going to persevere and do the whole calculation of self-similarity of the second kind. Namely, we can very easily solve this equation. Easiest thing would be to write this equation as treat psi as the dependent variable and use the independent variable that makes it linear. And I can solve this equation exactly. And there are two types of solutions. For alpha equals 0, I get a linear. And then the other solutions are like that. This is an exact solution to this ODE. But for this similarity profile to be regular at the origin, 1 plus 1 over alpha has to be an integer. And not only that, it has to be an odd integer. Otherwise, won't be a one-to-one function. It would fold. So from the condition that 1 plus 1 over alpha be an odd integer, I get a semi-infinite sequence of alphas starting from I equals 0. So again, I get not one solution, but in fact, I get an infinite sequence of solutions. And as Marco has indicated, the question is which of these solutions is selected. So let's deal first with this solution here. And okay, so the observation is that this follows from regularity at the origin. To deal with the solution alpha equals 0, I have to invoke the matching condition Marco has mentioned already. Namely, we have to make sure that the singular evolution near the singular point x equals 0 is consistent with a smooth evolution of the solution at some distance from the singularity. In other words, if I'm positioning myself at some finite distance x away from 0, this variable has to remain finite. Otherwise, the singular evolution would not match onto a smooth outer solution, or in case this would go to 0, this would correspond to the singularity not occurring at a point, but along a whole line. So I have to invoke this condition here. And clearly, the solution for alpha equals 0 does not satisfy this condition, because if x is finite, this will go to infinity. So from the matching condition, I can exclude the existence of these alpha equals 0 solutions, because this becomes infinite for t prime going to 0, and I can triumphantly announce all the possible solutions to this shock problem with a given set of scaling exponents. And so next we must decide which of these scaling exponents is selected. And to select the scaling exponents, I have to investigate the stability of these solutions. And that is at first a very difficult problem, because these solutions are highly time dependent. So the solution to this is to pass into a space of self-similar variables and introduce the dynamical system Marco has mentioned, where for consistency reasons, I introduce a new time tau, which is minus the log of my original t prime. So as the singularity is approached, tau goes to infinity. So at first, it seems that this is no advantage overall, because I started with a PDE in t and x, and now I have another PDE in tau and psi. But the great advantage of what I've done here is that my similarity solutions we saw on the earlier slide are solutions to the right-hand side of this equation. In other words, there are fixed points of this dynamical system, and fixed points are, of course, much easier to investigate than time-dependent solutions. So to find the stability of these fixed points, I have to do an eigenvalue analysis of these equations around this fixed point. So schematically, I'm in some high-dimensional phase space of all possible profiles. Let my similarity solution be this fixed point here at the origin, and I would like to know whether I'm attracted to this fixed point. And I do that by expanding to linear order around this fixed point. So I'm investigating the stability. So here's my full solution. U bar is the similarity solution I'm interested in, and I'm allowing for a small perturbation of amplitude delta, which is e to some eigenvalue nu tau times the eigenfunction p of psi. And as usual, what I'm interested in is to know whether the real parts of these eigenvalues nu are positive or negative. If they're all negative, this situation is stable. If some are positive, then the corresponding eigen profile is unstable. And in this very simple example, I can easily write down this equation to linear order. So here I simply plugged in this expression here into the dynamical system from the previous slide, and here is the eigenvalue. And this eigenvalue equation can again easily be solved exactly. The trick is once more to replace this independent variable by u bar as the independent variable. And you get a solution, which I don't think I've written down, but it has a similar structure to solutions I showed you earlier. And the key is to look at the behavior of this solution at the origin. And the condition for the P here at the origin to be regular is once more that psi to some exponent be an integer. And from this condition, from this regularity condition at the origin, I can calculate the eigenvalue. So now note that I have two indices here. I have an index I as previously, which counts my different similarity solutions. And for each I, for each similarity solution, I have a sequence of J's, which number the eigenvalue. And a quick analysis of this sequence reveals that if I equals 0, then all the eigenvalues are negative, and if I is greater, then there are positive eigenvalues. You have to be a little bit careful, as Marco, of course, pointed out. There are, in fact, even for I equals 0, some positive eigenvalues which come from the invariance of the equations under a shift in the origin x0 and t0. So I get exactly these trivial positive eigenvalues from this analysis. And I have to look at the other eigenvalues. And that shows me that there's only one stable solution, namely the one associated with I equals 0. And it carries these exponents, which are the generic values from the well-known classical shock theory. So now, after having developed some of these tools, I want to come back to some of the features I invoked on my very first slide. How can we work towards a complexity as you saw in this turbulent jet? So how can you produce structures which become smaller and smaller as you go down in scale? And here is a beautiful experiment, once more, of a drop breaking up. So this is a viscous liquid within another viscous liquid. The black is a liquid which has a much, much smaller viscosity than the outer viscosity here. And the result of this is that as this neck here breaks and starts to retract, it's much inhibited because there's a lot of friction with the outer flow. So here, as a result of that, I have a pinch-off event, which I labeled 1. But before this neck can retract completely, there is another breakup event, which I labeled 2. So in other words, I have gone full circle. I've gone through a sequence of profiles to reach the same initial state as before. And this repeats itself again before this neck here can retract. There is another pinch-off event. So this is a beautiful experimental realization of what Marco has explained and called a discrete self-similarity. So I see, if I always look at the same place in this sequence here, I see a self-similar evolution. But as I do this, as I go around the circle, I will see a whole continuous evolution of different shapes. And to explain this in a little more detail, I want to go back to the model system Marco has introduced and look at the breakup in the thin film equation. This is really pioneering work initiated by Marco. So what we have here is a thin film on top of a solid substrate. The thickness of this film is, I call H. It will be a function of a single variable X and T. So at the moment, I'm in one dimension. I will go to higher dimensions soon. And this film breaks because I'm including intermolecular forces which account for the attraction of different molecules, and this attraction leads to an attraction of this free surface to this solid surface down here. And so this leads to this extra term in the equation, which is of second order, but is unstable. And since this is unstable, it must be regularized by a higher order term, which is this fourth order derivative here, which comes from surface tension. And it's the interaction, it's the combination of these two terms which are responsible for the complexity. So Marco's idea was to look at this exponent n here as a free parameter. If n is large, that means that the interaction between the top and the bottom here is very local, because if h is just detuned a little bit from its minimal value, since I'm raising it to a high power, and it decreases, decreases very, very quickly, and I have a very local interaction. Under the condition of local interaction, I have simple self-similar solutions indicated here. So if n is about 1.7, I get exactly the type of solution I introduced before, which is a fixed point of my dynamical system, and is a in similarity space time-independent solution, which is simply rescaled as time goes on. However, if I make the interaction slightly more long-ranged, then I observe these instabilities, which make themselves known as side branches that suddenly grow on the side of this profile. A side branch grows, the side branch experiences another instability, and so on and so forth in a periodic sequence. So in other words, you have a limit cycle. So here, this means you have a limit cycle in this dynamical system. So here it is once more. My ansatz is that H gets rescaled as before by factors T prime to the alpha and T prime to the beta, but I allow this self-similar function now to be also a function of tau. And so this is the dynamical system which Marco and colleagues have studied. And they were able to identify the mechanism by which such a limit cycle is born, namely the Hopf bifurcation. So here is a typical result for a sequence of profiles. I can look at this in different ways. As the profile evolves round and round, I have to catch it in the same phase of its evolution. One way of doing that is to just always, for each round, just take the profile taken when it has its smallest minimum value. And you see it superimposes beautifully and looks like an ordinary self-similar solution. But it's not self-similar, as you can see here. Namely, in reality, this minimum of my F evolves in time, evolves in tau. Here, I've simply shown this dot and this dot, but in reality, I'm going to this whole sequence of profiles to eventually come back after a period T to the original profile. So the way to think about it, in the spirit of this drop breakup experiment I've shown you, the way to think about it is that in this drop formation experiment, you have a sequence of generations of small drops which are formed, and for each generation the size decreases exponentially as given by this period T. Or in the spirit of the thin film equation, the sizes progress geometrically as you would in a simple fractal, which is characterized by a single scaling exponent. But there are very strong indications that if you decrease this parameter n even more, this limit cycle I was talking about itself becomes unstable. And the dynamics, this evolution of these profiles becomes chaotic, which means that for each stage of the evolution, there are constantly new structures being created, which means that if you look at the scaling properties of these structures created at smaller and smaller scales, the scaling exponents are constantly changing, so that we expect that the scaling of this fractal object will be different at different locations in space. In other words, this is a model for what is called multifractal scaling. So this gives an indication of how random structures, somewhat similar to this turbulent jet you saw, are produced as you proceed in scale. The other question we still need to answer is how a spatial structure is generated from this. And this is the last part of my talk. I'm going to talk about the generic mechanism by which what we've learned in one dimension gets translated automatically into space once you consider the higher dimensional equivalent of my equation. And here I again have a very qualitative picture taken from the physics of shock waves. So this is the sequence my colleague Patrice Legal found on the internet. There are very few experiments in this area. So this shows a condensation cloud, which is a pretty good indicator of the transversal extent of my shock. So far I've looked at a one-dimensional situation, so it's in some sense infinitely extended in the transversal direction. But in reality, of course, the shock will start at a point at the most optimal conditions. So that's this point, and that as time progresses, the size of this cloud increases. And if you plot L here, the size of the cloud as a function of T prime, you see this is a square root. So why is it natural to have a square root? Well, as I said, the singularity starts at a point where the initial conditions are such that they are most conducive to the formation of a singularity. But if I detune a little bit in the transversal direction, the conditions will no longer be optimal. So when does the singularity occur if I detune by some distance y in the transversal direction? Well, this detuning must be of the form ay squared, because if it were linear on one side, it would have occurred even earlier. Whereas I insisted that t0 is the time at y equals 0 where the singularity occurs first. So you see from this that generically the detuning, the behavior of the solution in the transversal direction must go like t prime to the 1/2 if I take the square root of this equation here. So this is what we will try, and we will apply it to the thin film equation. So this is the thin film equation once more, but written in arbitrary dimensions. I will be looking at 2 dimensions, which just means I have a nice liquid film on a table. And the same mechanism of instability. So I will create holes in this film. How do I create holes in this 2-dimensional film? And the idea is the following. Emboldened by my argument, I postulate that I have a second self-similar variable, eta, such that the variable in the transverse direction scales like t prime to the 1/2. If I make this ansatz and plug it into the equation, I get the following structure. On the right-hand side, I expect the derivatives I have here, which are in both spatial x and y derivatives, be dominated in a one-dimensional, in one direction, simply because of the character of the initial condition. There will be one direction in which the singularity occurs earliest, and the corresponding derivatives in this direction will dominate the other derivatives. So as a result from this argument, I only have the most singular derivatives on the right-hand side, and I have one extra term, this one here, which comes from the behavior of my solution in the transversal direction. And this equation I can easily solve, and I get the solution h of psi and eta given in terms of the solution of a problem I know already, namely the solution of the one-dimensional film evolution problem. The only thing that occurs owing to this additional variable, to this additional transversal dimension, is that the argument of my one-dimensional solution gets rescaled as a function of this parameter eta. But once I know the one-dimensional problem, I can see how by this formula, the full solution is unfolded into space. So let's illustrate that with a numerical simulation of the thin film equation. So here once more is the solution, which with an H1, a similarity solution I know. And this is what happens. This initial condition evolves into two sharp peaks, which are unfolded in the transversal direction. I should say that for clarity, we're plotting not h, but 1 over h. So the places where h goes to 0 are exaggerated. They appear as peaks. So what I'm saying is this: if I around the center look in the direction of x or of psi here. Oh, this didn't turn out right. I see. So you're not seeing that. There's a muddle here in the slides. So if I look in this direction, I simply see this one-dimensional solution. By contrast, if I go into the transversal direction, I see the same thing, but at earlier and earlier times in the evolution, in this one-dimensional evolution. And if I superimpose these profiles, I see a parabolic behavior, just as we predicted from my general detuning argument. So this becomes even more interesting if my H1 is not a fixed point, not a constant function, but itself time-dependent. In this case, the solution of the equation is this here, which is a scrambling of space as a function of the transversal variable, but also of time. So I take my original solution and it's all mixed up as I go into the transversal direction. So in one picture, I see the whole evolution of my one-dimensional solution at the same time, because it's unfolded into the transversal direction. So here are some checks that indeed, if you look at the solution at the center, at y equals or eta equals 0, I get the original periodic orbit expected from a discrete self-similar solution. But if I look at a snapshot in space, I can see that I already get quite a complicated and scrambled and fractal picture in space, where in one picture you see all the stages of evolution, depending on where you are in space. And this becomes even more interesting if you go to even a smaller n, that is to even more long-ranged interactions. So the computer decided to turn this. So here you see the one-dimensional solution. Here you see a chaotic evolution, which means that as you go down in scale, you constantly create new features. And here is the same thing unfolded into space. And you see a completely scrambled. If you look at different places in space, I get a random distribution of different behaviors in space. finally, I can look at this in one other way. Here, I've looked at the evolution of a single peak and followed its chaotic evolution. But another salient feature of chaos is, of course, sensitivity to initial conditions. So in other words, if I ran many of these simulations in parallel with slight errors made by the computer, I will always get something else. And this is shown in this picture. So here we have much the same initial condition, but we have tuned parameters that the initial distribution is unstable to very small wavelengths on this picture. In other words, starting from this initial condition, I have many, many evolutions of the same dynamics with only slightly varying initial conditions. So you can see here very clearly from this checkerboard pattern, what's the characteristic unstable wavelength of the evolution. But in each of these sets here, you see something that is different because the evolution depends sensitively on exactly what you do with your initial condition. For example, there's an extremely hot spot here, which does not repeat in the same way. So indeed, here you seem to have admittedly very simple example, but nonetheless an example of randomness, which evolves both towards smaller scales and gets unfolded into space, much similar to this turbulent jet I showed you earlier. Thank you very much.